Today's lesson is called the greatest common factor. We're going to go over our vocabulary words first. Our first term, common factor. Now, by now, I'm sure that when you hear the word factor, you right away think of a multiplication problem. The factors are the numbers that you multiply to get your product. A common factor is a whole number that is a factor of two or more non-zero whole numbers. So for instance, the number 4 and the number 6 have a common factor of 2 because both can be divisible by 2. 2 times something equals 4, 2 times something equals 6. Our second term, greatest common factor. It's the common factor of 2 or more numbers that is the greatest. So if you were to list all the factors of a number, or 2 numbers, or even 3, and you looked at the factors that they had in common, the one with the highest value that they both or all 3 have is your greatest common factor. And then our third term is relatively prime. Relatively prime means it's used to describe 2 numbers whose greatest common factor is 1. So in other words, you have 2 numbers that might be composite, but that they don't have anything in common except that they're both divisible by 1. Now before we start working on our 5 examples, I want to give you a list of the steps you need to follow in order to find the greatest common factor. So there are 5 steps that you follow to find the greatest common factor, which we abbreviate as capital G, capital C, capital F. You'll see this a lot. Greatest common factor. So the first thing we have to do to find the greatest common factor is what we learned in the lesson before this one, using a factor tree to get the prime factorization of each number. So if you need to find the greatest common factor of 2 numbers, you'll make 2 factor trees and then list their prime factorization. But the difference is that you will not use any exponents. After you finish your factor tree, in rows, just as we did in the other lesson, you will list the prime factors in ascending order. And again, we're going to not use exponents. So if there are 3 2's, we will keep 2 times 2 times 2. After you list your prime factors, you will circle the common factors. Then you'll make a multiplication expression using the common factors, and then we will evaluate. After you've copied these steps, we'll go on to example 1, where we will in fact follow all 5 of these steps. Okay, so here we have to find the greatest common factor of 48 and 36. And as you can see, I started us off with our factor trees. Now remember, when we're making our factor trees, the point is to gradually work from our original number down to all the prime numbers that when multiplied have a product of here 48. So what we're going to do is pick any 2 factors of 48. So I'll start with 6 and 8. And remember, we do not stop until we have a prime number at the end of each limb. 6 is not a prime number, so we'll add 2 more branches to it. We make 6 by multiplying 2 and 3. 8 also is not a prime number. 2 factors of 8 are 2 times 4. Now here, the 2 is prime, so we'll bring it down. The 3 is prime, and so is the 2. The 4, however, isn't yet. We make 4 by multiplying 2 twice. So we have the prime factorization of 48. Now we'll do the same thing for 36. 2 factors of 36 are 4 times 9. 4 is not a prime number, so we'll break that down to 2 times 2. 9 also is not a prime number. That becomes 3 times 3. So we've completed our first step, make our factor trees. Our second step is to make a row of the factors in ascending order. Here's our 48. We have 4 2s and a 3. We'll do the same thing for 36. That needs to go directly underneath the 48. We have 2 2s and 2 3s. Our next step from the list that you copied is to circle the factors that they have in common. Here's how you do that. They both have a 2. They both have a second 2. Make that easier to see. And they both have a 3. So they have 3 factors in common. A 2, a 2, and a 3. Our next step is to make a multiplication expression using only the factors that are in common. So we'll take this 2 that we circled, multiply that by the next 2, and then by the 3. And our last step is to evaluate. 2 times 2 is 4. 4 times 3 is 12. So the greatest common factor of 48 and 36 is 12. That means that of all the numbers that get multiplied to make a 48 and to make a 36, 12 is the highest. We're going to do the same thing for 25 and for 32. We need to find the greatest common factor. Our first step is to make factor trees. 25 can be made by multiplying 5 times 5. They're already prime numbers, so we're done with that tree. Next we have 32. This will take a little longer. 32 can be made by multiplying 4 times 8. 2 is not a prime number, so that becomes 2 times 2. The 8 is also not prime. That becomes 4 times 2. We'll bring down all our 2's because they're prime numbers. And then finally, we'll take our 4 and make that 2 times 2. Next, we'll list our factors. For 25, we have 5 times 5. And for 32, we have 2 times itself 5 times. Our next step is to circle the factors that they have in common. Well, if we look, they don't have any factors that are in common. The only factors of 25 are 5, and the only factors of 32 is 2. So what we do is we call this relatively prime. These two numbers, even though they are not prime numbers themselves, in isolation, together, the only thing they have in common is that they're both divisible by the number 1. So we call them, again, relatively prime. Now, for example, 3. We are going to take the same process, the same steps, to find the greatest common factor of monomials. You'll remember monomials are terms that are made by multiplying a whole number and a variable with a positive whole number exponent. Now, for the sake of room, what I'm going to do is, no, I think we'll have room. So the 24y squared, remember we factor the 24 to 6 times 4. This might be a little bit too small, but I hope we'll get it right. The 6 will be 2 times 3, and 4 is 2 times 2, which makes the factors of 24y squared 2 times 2 times 2 times 3. So we have our number down. And what about our y squared? That means y times y. Next, we'll factor 8y to the 4th power. Well, we can make an 8 by multiplying a 2 times a 4. We'll bring down the 2 because it's prime. 4 becomes 2 times 2. So the factors of 8y to the 4th power are 2 times 2 times 2, and then y to the 4th is represented as y times itself 4 times. And then our third term, 12y cubed, our 12 we'll call 3 times 4. We'll bring down the 3 because it's prime. The 4 gets broken down into 2 times 2. So our factors of 12y cubed are 2 times 2 times 3, and then 3 y's. Remember, we list our numbers in ascending order. That means from least to greatest. And then after the numbers, we follow with the variables. If you look down your list of steps, you'll see that we are up to the part where we have to circle what's in common. Now this gets a little tricky, but definitely doable. We have to make sure that they are common among the 3 numbers. So here I see all 3 have a 2. All 3 have a second 2. And those are the only numbers that they all have in common. So let's jump ahead to our y's. Here's one set of y's that's in common, and another. Now we'll make our expression, which will have 4 terms in it. 2 times 2 times y, which makes our greatest common factor. 2 times 2 is 4. Y times y is y squared, or y to the 2nd power. This is the highest term that can be evenly divisible into each of our 3 monomials. Now our 4th example also has monomials in them, but you'll notice that while in example 3 we had only one variable, the variable y, these monomials have 3 variables, a, b, and c. Now what I did was I chose numbers, the coefficients of these monomials, to be very simple, because what I want for you to get right now from this video is understanding the steps, to know the process. If you know the steps, then later when you have more challenging numbers, you'll be able to readily apply what you know. So for the sake of space, I'm going to forego the factor trees. We know that 15 is the product of 2 prime numbers, 3 and 5. That leaves us with our a squared, which is a times b times c to the 3rd power, which is 3 c's. Next we have our 21, which also is the product of only 2 prime numbers, 3 times 7. We have 1a, b to the 3rd power, so times b times b times b times c times c for our c squared. Our next step, circle what they have in common. The only number they have in common is the prime number 3. And let's see what else. Well, notice that when I listed my variables, those are also in order. They both have an A, they both have one B, and they both have 2 C's in common. And we put those together in an expression. That becomes 3 times A times B times C times C, making the greatest common factor of these monomials 3AB C squared. And we have one last example, a word problem. I'll read it to you. A music camp has 32 vocalists, 16 drummers, 24 guitarists, and 16 bassists. What is the greatest number of identical bands that can be formed? Basically what we're doing is taking what we learned about finding the greatest common factor and applying it to a real-life situation. So what we're going to do is find the greatest common factor of 32, 16, 24, well, and 16 again. Now when you do this on your own, you will make your factor trees, but because I want to save some space and because you're familiar with that process already, I want to get right to just listing the factors. 32 is found by multiplying 2 times 2, which is 4, times 2, which is 8, times 2, 16, times 2, 32. So 2 to the 5th power is 32. 24 is 2, times 2, which is 4, times 2, which is 8, times 3. 8 times 3 is 24. And 16 is made by multiplying 2 times itself 4 times. Now we circle what's in common. One, 2, 3. They all have 3 2's in common, and there's nothing else in common among all 4 numbers. Next, we make our expression. 2 times 2 times 2, which is 8. So the greatest common factor of the numbers 32, 16, and 24 is 8, which means they can make 8 identical bands. But let's take this a step further. What if you were being asked, well, in your 8 bands, how many vocalists are there? How many bassists? How many guitarists? And how many drummers? Well, here's how we would do that. So let's just recap. At the camp, there are 32 vocalists, there are 16 at the peak drummers, 24 guitarists, and 16 bassists. Now we know that we can make 8 identical bands. So if we wanted to know how many of each group of people, each group of musicians there were in each band, what we would need to do simply is divide each of these numbers by 8. So these 32 vocalists have to be divided evenly into the 8 groups. So that means each band will have 4 vocalists, 2 drummers, 3 guitarists, and 2 bassists.